So we're moving on here. It's problem 21. Actually, let's do 19 through 21. Because they're all the same, basic same problem. So it's this pea pod experiment in terms of dominant, recessive. It says Mendel found no dominance in snapdragons in contrast to peas with respect to red and white flower color. When pure red and pure white parents are crossed, the resulting R, capital R, small r, which is the dominance, one for each gene, produces second generation offspring that are pink flowers. These second generation pinks, however, still carry one red and one white gene, so when they're in the cross with the third generation is still governed by table 3. Find the probability for third generation snapdragons. So let's go back and look at table 2. So what it's saying is that let's make sure to do this here. So you still have this table after the first generation. So what you basically have is, let's say this is a red I'm trying to make sure I'm doing this right here. So what we're going to do is we are going to cross basically, well, actually the first case is you're going to cross the red and the white. And the red has two dominant red genes and the white has two dominant white genes, or white genes. So this will give you red and this will give you white. And then if you get one of each, because there's not any dominance, then you're going to get pink. So you get a combination of the two. Now if you were, let's say red were dominant, then you would still get red under these circumstances. But in this case you get pink. So what that means is you're going to have one dominant and one recessive gene. And so let's say you have, this is your one pink flower which has one red gene and one white gene, and here's another pink flower which has one red gene and one white gene. When you have these two reproduce, two pink ones reproduce, you may get two red ones. So you may get that, you may get that, you may get that, or you may get that. So two pinks, the chances are that of the occurrences, there are 4 possible occurrences, so 4 total occurrences. One of those occurrences is red. That's when you get the 2 red genes together. There are 2 pink options. That's when you get a red and you get a white gene. And the third one is white. And there you would have 2 of the small R ones. So this plus that equals a total. So now we should be able to answer the questions. So what's the probability, this is number 19, what's the probability of getting a red carnation? Well, 1 out of the 4 is a red choice, and so the answer is 1/4. Number 20 asks what's the probability of getting pink, and there are 2 cases. I can get a red from one, big R from one, and small r from the other. I can do it the opposite way around. So there's 2 of those choices, and so I get 2/4 or half, and then 21 is the probability of getting white. There's only one of those out of the 4 choices, so I get a quarter. So it's a quarter and a half and a quarter for this particular problem. Now the first case, when we I had to plug in my thing here. My headphones, the battery's getting down. When we did the red with the white, there really was only, they'd all be pink. So you cross a red with a white, you get a pink. If you cross 2 pinks, the chances are a probability of half that you're going to get a pink, probability of a quarter that you get a red, and a probability of a quarter that you get a white. Okay, let's go to the next one on the list, which is 25. So this is a cystic fibrosis problem. So it says cystic fibrosis is one of the most common inherited diseases in North America, occurring in about 1 of every 2,000 Caucasian births and about 1 of every 250,000 non-Caucasian births. Even with modern treatment, victims usually die from lung damage by their early 20s. And so you actually, they do this test, blood test, and both of our daughters have a recessive gene for cystic fibrosis. We don't know which parent it came from, but it really doesn't matter because we're not having more kids. But our children now know that they do not have a recessive gene, so they didn't have to worry about it. You also, well, actually, sorry, that's not true. Their children will get a test before anything they decide to have children. Both their husbands did not have a recessive gene, and therefore there was no chance of the offspring having cystic fibrosis. So anyway, it says, find the empirical probability that cystic fibrosis will occur in a randomly selected infant among non-Caucasians. So these are just using the probability question. So let's do 24 through 26, since they're basically the same thing. So for Caucasians, it says 1 out of every 2,000. So that's the fractional equivalent. And if you do the math there, you'll get 0.0005. So that's the probability. For non-Caucasians, it's 1 out of every 250,000. So you create the fractional probability, and then you can do the math. Use your calculator, and you get a pretty low number here. And then it says among 150,000 North American Caucasian births, about how many occurrences of cystic fibrosis would you expect? So what you do is you can use this number, because X over 150,000 has to be equal to the number that we got in this. So you can solve for X by just multiplying those two things together. So we get 0.0005 times 150,000, and you get 75. Okay, so move on here. I think I've already talked about cystic fibrosis in class. So, okay, now we've got actually more questions here. 27. So what we're doing, 25, 29. Yeah. So let's just go ahead and do these 3 because it's not that long. 27 through 29. So it says, suppose that both partners in the marriage carry cystic fibrosis carrier, a rare occurrence. Construct a chart similar to Table 3 and determine the probability of each of the following. So it's kind of like the recessive P diagram. So what you have is you would have two parents. And if they both contain a recessive, which is the small r, they would have a situation like that. So if they both get the dominant gene, which is the non-cystic fibrosis, everything's fine and their offspring will be fine. In these two cases, you get a recessive and a dominant, and then finally you get two recessive genes. This is the cystic fibrosis. These two are carriers, so they don't have it. But if their offspring were to have children with someone who also had a recessive gene, then that couple would have a similar type of probability. So so their first child will have the disease. What's the probability? Well, this is the only one this combination gives you. So there are 4 possible gene combinations. So the probability of having is going to be the number of occurrences divided by the total number of possibilities. So it's a quarter. Even that's just a 25% chance. The probability of being a carrier is going to be these 2 cases. So there are 2 of those out of the 4. So the probability is 1/2. And then 29, the probability of not having nor a carrier. So it's not having and not a carrier. That's going to be equal to 1/4 as well. And then you add these 3 together, you get 1. It's got to be one of these 3 choices. So what happens is, let's just talk about the case where one of you is a carrier and one of you is not a carrier. So if that case, what it looks like is you'll have 2 R's for the parent that's not the carrier. You'll have a dominant and a recessive gene for the one that is a carrier. So here you get 2 R's, 2 capital R's, and here you get that situation. So there's a 50% probability that the offspring, like my grandchildren, will not be a carrier, and a 50% chance or 0.5 probability that they will be a carrier. Okay, 33. So here we have sickle cell anemia. Sickle cell anemia occurs in about 1 of every 500 black babies' births and about 1 of every 160,000 non-black baby births. It is ordinarily fatal in early childhood. There's a test to identify carriers. Unlike cystic fibrosis, which is recessive, sickle cell anemia is co-dominant. This means that inheriting 2 sickle cell genes causes the disease, while inheriting just 1 sickle cell gene causes a mild, non-fatal version. And I guess if you get 2 recessive or 2 of the other kind, then you don't have it at all. So it says in exercises 33-34, find the empirical probabilities of the given events. So let's just do all 3. Let's do all 3 of them again. So you end up with a similar table to what we had before. As I said, So you've got yeah, to answer those questions, you know, you have a couple more possibilities. We'll talk about those in a second, but we're just answering the questions they have first. So the probability 33 of just a selected black baby having sickle cell anemia, it says it's a 1 out of 500. So you just divide 1 by 500, which is 0.002 probability. The probability of a non-black baby having sickle cell anemia, again, it's just 1 over 160,000. I think it was 160,000. And that gives you a number 0.0000. How many zeros? 0, 6. And 35 among 80,000 black babies, how many would you expect to have that? So it's the same kind of deal. It's going to be X over 80,000 equals 0.002. So you multiply 80,000 times 0.02, and you get 160. That's your answer. Now, in the case of you know, the sickle cell thing, is you could have a parent that doesn't have any recessive genes, and then you have one that has a combination, so they have a mild form of sickle cell anemia but not fatal. What you would get if you do these multiplications together is you would get that situation. So if they have the mild case and they have children with somebody who doesn't have it at all, there's a 50% chance they won't have it at all, and a 50% chance their children will have a mild case. Then you have the case where you have two people who have a mild case and they have children. So you would get dominant and recessive, and then you get this arrangement. So this would be none. So they have a 1 out of 4, a 1/4 probability of not having any problem. You'd have a 50.5 probability that they would have a mild case, and a 25% probability that they would have a fatal case. And actually that's what problems 36 through 38 do the same thing. So 36, it says there, if you have a condition where parents both have the sickle cell trait, so it's this case. So the probability of we'll have sickle cell anemia will be this. Sickle cell trait will be this, and the healthy will be this. So it's a quarter, a half, and a quarter are the answers for 36 through 38. So the probability for this one have full-blown, it would be 1 out of 4. 37 is the probability of trait, which means that they have it but it doesn't kill them, and you get 2 out of 4, which is 1/2. And then 38, probability of nothing, not a trait, not having it, that'd be 1 out of 4, and that works.